Good evening. Today we are going to start with the last session of our ray optics where we deal with optical instruments. We need to deal with simple microscope, compound microscope, telescope, two types, the refracting type and the reflecting type. Today in our session we'll discuss about the simple microscope and the compound microscope. Now, a simple microscope is just a magnifying glass like this. You would have seen this such a magnifying glass where you can use this magnifying. So this is just a normal convex lens. You can use this magnifying glass to enlarge. Maybe you are trying to read something very small. So if you use a magnifying glass, you can see it enlarged. Okay. So this is what we have as the simple microscope. Now, for the convex lens in 10th standard, you have learned ray diagrams for 6 positions of the object, where you're keeping the object initially at infinity, then you bring it closer. So, as you bring it closer, the next position you have learned is you keep the object just beyond C, then at C, then you bring it closer between F and C, then at F, and then finally you keep the object between the focal length and the optic center. Now, if you go back to all those ray diagrams, you will notice that only for this ray diagram, where this position of the object, where you have put it between focal length and the optic center, the image will be enlarged and erect. You have other positions which give you an enlarged image, but those images will be inverted. So when you're using it as a magnifying glass, you definitely want your image to be erect, because if you're trying to read something, there's no point in seeing it inverted. So that is why a convex lens will behave like a simple microscope, which is a magnifying glass. Only when you put the object, when you're trying to read something, if the letter that you're reading is between the optic center and the focal length, then the final image will be, you can see it enlarged and you can also see it erect. So this is the ray diagram for a simple microscope, which you already know from 10th standard. Now, you have learned 2 formulas for magnification. One called the linear magnification in terms of height of image and object, which is Hi by Ho. You also have learned magnification of a lens in terms of image distance and object distance, V by U. We now in 12th standard also define magnification of a lens as beta by alpha. Let me first tell you what is alpha. Okay. Now suppose I'm looking at the pen. No lens, nothing. I'm not magnifying it. I'm just looking at the pen like this. You know that it should be at least at 25 centimeter, which is called the least distance of distinct vision. For you to see something clearly, it should be at least at a distance of 25 centimeter. Then from there, you can also see if this object goes on to infinity, it's another position where you can see the object clearly. Now, at a distance of 25 centimeter, let's take one ray coming from the bottom, from the base of the pen to my eye, another ray coming from the top of the pen to my eye, and the angle that it subtends at my eye when the object is kept at distance 25 centimeter is what you call as alpha. So alpha, basically, if you're showing it with a diagram, this is the object, this HO object, which is kept at 25 centimeter, which is what you call as D. Whatever angle it subtends at the eye without any lens, no magnification, that is what you call as alpha. So alpha is angle subtended by the object at the eye when it is kept at D, right? Now, suppose you are going to use a lens and magnify this. So, we have a magnified image if this is kept between the optic center and the focal length of the lens. So, that magnified image is what we have here. Now, to see this image from here, so you are looking from here, to see this image clearly, it should be at least at a distance of D, which is again 25 centimeter, otherwise it's not clearly seen. From D, you can shift this object towards infinity, still it will be clear vision for you. Always remember normal adjustment, that is when you can see the object clearly at 25 centimeter, But if this is formed at infinity, if the image is formed at infinity, you can view the image with your eye muscles will be relaxed, and it's a more comfortable viewing if the final image is formed at infinity. So here beta is this angle, which is defined as, if you look at this big triangle, you will see that this is the angle subtended by the image when the image is formed at D. So beta here we define as angle subtended at by HI, the image, at the eye when formed at D. Right. So this is without any magnification. This is after magnification. So it's like this. You use the object, it subtends an angle alpha at D. Use a lens, magnify it, let the image be formed at D. Whatever angle it subtends at my eye is what you call as beta. So you may define magnification as beta by alpha, right? Because suppose imagine that the image is subtending a larger angle, let's say 40, and the object is subtending an angle of 20. So 40 by 20, which is 2 times magnification. So if the height of the object is 2 centimeter, twice magnification would be 4 centimeter. So this is magnification beta by alpha. So from the figure, beta I can write as, from this big triangle, tan beta for small angles can be approximated to beta. So tan beta is opposite side by adjacent side. So that's HI by D. So we have HI by D here into alpha from this. Tan alpha approximated to alpha. Opposite side is HO by D. So this will be D by HO, which is in 10th standard you have already learned as magnification HI by HO, which is also equal to, we know, V by U for lens. Image distance is V and U is the object distance. Now this I can write as V into 1 by U, right? Now from the lens formula, 1 by F equal to 1 by V minus 1 by U. I can substitute for 1 by U as 1 by V minus 1 by F. So I am going on to write magnification as V into, instead of 1 by U, I will write it as 1 by V minus 1 by F. Or, see, where is our image formed at D? So when you measure the image distances, you know the sign convention. That is, if ray of light, incident ray is taken, the direction of incident ray is taken to be the positive direction. So in our case, the incident ray is towards the right. So positive direction will be the right. So if you are measuring from the optic center to the left, you need to take it as negative. So your image is here. So from the optic center, we are measuring to the left at a distance D. So we may take V as minus D, which gives us for one magnification as V. Let me write it on top. So magnification will be from here. Okay. This is, I am opening the bracket. So V into 1 by V will be 1. Then we have V by F. So 1 minus V by F. This is equal to, I am going to substitute for V as minus D, which gives me 1 plus D by F. So this is another new formula that we have introduced for you in class 12 for magnification. You already knew linear magnification has HI by HO, which is, we know, equal to V by U, image distance by object distance. Now in 12th standard, we know magnification can also be defined as angular magnification, beta by alpha, which in terms of the focal length is 1 plus D by F, where D is just a number, 25 centimeter, and F will be the focal length of the lens that you are using. So this is the magnification if your image is formed at D, least distance of distinct vision. I told you, for more comfortable viewing, you can have your image formed at infinity. Let's see what will be the magnification if it's formed at infinity. So the ray diagram will be different. You will now have to bring your object closer to the focus, because you know if the final image has to be formed at infinity, the object has to be at the focus, right? So we have a lens here, principal axis, and I am bringing our object was before in between F and optic center. Now I'm pushing it very close to the focus so that our object almost at the focus, one ray passing through the optic center, the other ray will go parallel so that these two will appear to meet at infinity. Okay. Now this is HO and your image is somewhere at infinity. So now what did we define beta as? Beta is the angle subtended by the image at the eye, right? So here this angle is what we call as beta because whatever angle subtended by the image at the eye, that is what we call as beta. But from this small triangle, we may also write this beta to be equal to, this small triangle tells you that it is opposite side by adjacent side, which is HO by F, right? So instead of taking the image at infinity, you can get the angle beta from the smaller triangle, which is HO by F. The alpha is the original, without any lens, alpha is always the same, which is HO by formed at D. This one. So now magnification is beta by alpha, which is equal to HO by F into D by HO, and we see that then this becomes D by F. So remember, two formulas we have introduced for you for magnification now. One is if the image is formed at D, then the magnification is 1 plus D by F. If the image is formed at infinity, the magnification is less by unity. It is simply D by F, not 1 plus. So even though the magnification is lesser when the image is formed at infinity, I told you it's more comfortable viewing because your eye muscles are in relaxed position, and so this is at infinity, more comfortable viewing, but the magnification is less by unity. So this topic is important because when we learn about the microscope, compound microscope and the telescope, the second lens in these instruments behave like a simple microscope. So whenever you think about a lens behaving like a simple microscope, there are a few things that must come to your mind. One, when does this behave as a simple microscope? Your object should be between optic center and focus. Then what about the magnification? 1 plus D by F if the image is at D, and 1 plus simply D by F if it is image is formed at infinity. Also remember, the final image is formed on the same side, right? It is magnified and erect and it's formed on the same side. So now we go on to the next instrument that we are going to discuss is the compound microscope. Now in the compound microscope, a simple microscope you saw there's only one lens. But in the compound microscope we have two lenses, one called the objective and the other called the eyepiece. Now both these lenses will magnify, and therefore we have higher magnifications possible in the compound microscope. So first, this is a compound microscope. We are going to draw the ray diagram, very important. Ray diagrams, microscope. Okay. So you must have used this compound microscope in your 10th standard biology lab, where you look through the microscope at some, probably you must have looked at onion cells or cheek cells, where you have a long microscope tube. There's one lens where you're looking through it, and that lens close to your eye is called the eyepiece. There's another lens which is close to the object you're looking at, the small cells that you look at. That lens which is close to the object is what you call as the objective. So first we have the objective, which is the smaller lens, objective, and then I'm drawing the principal axis, and this is the objective. Okay. So the focal length of the objective I'll note as FO, and this, let's say, is 2FO, 2 times the focal length of objective. You keep the object between F and 2FO. One ray of light, as you know, will pass through the optic center, no bending. The other ray, parallel to the principal axis, will pass through the focus on the other side, forming the first image. So this is the focal length on the other side. So this is where the first image is formed, that is the image of, which I call as H dash. This is the image of the objective. Now this image will behave as the object for the eyepiece. So remember, the first image formed by the objective will act as the object for the eyepiece, and the eyepiece in this compound microscope will behave like a simple microscope. So I told you, whenever you know that a lens behaves like a simple microscope, the condition is the object must lie between the optic center and the focal length, right? So I'm going to draw the eyepiece, which is a larger lens. So this is the eyepiece, and we see that this is the optic center. So this image, which is going to behave as the object for the eyepiece, must lie between the focal length of the eyepiece and the optic center. So that's why I've drawn this FE here, so that you will see that this is between focal length and optic center of eyepiece. Now we know one ray will pass through the optic center, the other ray will pass parallel to the principal axis. They will diverge, and so you'll have to extend it back to find out where it would have met. Remember, we did that here for this single lens here. If this is between the focal length and optic center, this ray of light will pass through the optic center. The other one they'll not meet on the other side because they'll diverge. So you extend it back to find out where it would have met. That's what we're going to do here also. So we have one ray passing through the optic center, the other ray parallel to the principal axis but diverging, so that these two will not meet on the other side. So you extend it back to find out where it would have met. Okay, right? I would have liked to use a scale and all that. Okay, so this is where they would have met, and this is where we will have our final image. Final image. Okay, this is what I'm going to call as H double dash. This will be the object height. Then this is the first image of the objective, which behaves as the object of the eyepiece, and the H double dash is the image of the eyepiece. Okay, and this, you're looking at this image from here. This is your eye. So I told you the final image should be formed at D or at infinity. So since these two are meeting here, this distance from the lens must at least be equal to D, this distance. Only then when you look from here, you can see a clear image. Okay. Now, when there are two lenses, please remember that the total magnification will be the product of the two. This we have discussed in the last session when we did power. That magnification is MO into ME, where MO is the magnification due to the objective and ME is the magnification due to the eyepiece. So you see here there is double magnification. One magnification done by the objective, a second magnification done by the eyepiece. Now MO, we know for any normal usual simple convex lens, you know the magnification is V by U. So I may write MO as VO by UO, because for this lens, this is the image, right? So this distance from the lens to the right, this is what we have as VO, and your object is here. So from the lens to the object, this is minus UO because you're measuring it from the lens to the left. So this is minus UO, and ME, we know that this is behaving as a simple microscope, I told you, whose final image is formed at D. That we have already derived in the previous topic as 1 plus D by F, right? So ME will be, because the eyepiece is behaving like a simple microscope and the image is formed at D, we may write ME is 1 plus D by FE, where FE is the focal length of the eyepiece. This is when image is at D. Final image is at least distance of distinction. So that I may write the total magnification as VO by minus UO into 1 plus D by FE. Okay, now also we need an approximation. This is the formula that you will use when you do problems, numerical problems, where VO is this distance of the image from the optic center of the objective, and this is UO is from here to the object distance of the objective. Okay. And D is 25 centimeters, FE is the focal length of the eyepiece. Now here we may take an approximation. See, suppose you take, let me take away this. Suppose you take this angle as theta and this angle also as theta, because they are vertically opposite. Now this distance I am going to call as L, that is distance between the focal length of the objective and the focal length of the eyepiece I am going to take as L. So if you look at these two triangles, this height here will be the same as HO. This is going to be the same as HO, right? So from these two triangles, I may write tan theta is equal to, from this triangle here, tan theta is opposite side by adjacent side. I may write it as H dash by L. And from this triangle, I may write this as HO. That is, this height is HO by, this is the focal length here, right? From here to here, it is focal length. So I may write this as HO by FO. Or I may rewrite this as H dash by HO is equal to L by FO. Now this is important because what is H dash? Image height of objective. And HO is the object height of objective. We know HI by HO is magnification. So for the objective lens, we may also write this MO is equal to L by FO. We may write magnification of the objective as H dash by HO, which is L by FO. So if I go back to my formula, total magnification can also be written as L by FO into 1 plus D by FE. Okay? 1 plus D by FE. So here, let me go over this. So whenever the image is at D, we have two formulas. One is you may substitute this minus sign when you do your problems. You will take it as negative. So that then while you're doing your problems, you substitute it as minus UO. So this is MO into ME. For any normal lens, we know it is VO by UO. V by U, which for objective I wrote it as VO by U. And because this is behaving, your eyepiece is behaving like a simple microscope whose image is formed at D. We took it at D. We know this is going to be 1 plus D by F, and that's how we got this formula. Then we have this approximation where you may replace this VO by UO as L by FO. Now you will see that whenever you want high magnification, this FO and FE must be very small, right? Only then can we have a high magnification. So for compound microscope, both FO and FE are very small. FO will be less than FE also. So why we need to know that is because this FO and FE are very small, which means this FO will be close to this objective lens, FE will be close to the eyepiece lens, so that this L may be approximately taken to be the tube length. Tube length meaning the distance between the two lenses of the compound microscope can be taken to be L. The reason is, I told you, for all compound microscopes, since magnification should be high, FO and FE are very small values. FO is measured from the optic center to this, and FE is measured from the optic center to this. So FO is actually close to this and FE is close here. So this total distance between FO and FE, we may approximate it to be the tube length L, which is the distance between the two lenses in that tube of the microscope. So that is L by FO. Okay. So for application questions, you may use this formula. For numericals, you will use this formula. So for our session today, we'll stop now. Make sure that you know this ray diagram and the derivation. Thank you.